Good morning. Here we are, picking up again in Chapter 7. And at the end of the last lecture, we had started looking at springs. Actually, let me go back and review a bit of what we've already been looking at. We've been looking at energy transfers due to forces. So we're using forces to exert, the forces are exerting a force on objects, and those objects, as a result, could either be picking up speed or slowing down. So these forces could tend to speed up the objects or slow them down. Or it could be that these forces are used to oppose other forces. In either case, what we can do is calculate the energy transfer. Now, the energy transfers, we had started out by saying those were just force times displacement. But then we showed that the more general formulas involve taking something that we call a dot product. So we introduced the idea of a dot product, and that became our most general formula. Now the question may come up, well, which formula do we use, right? This is the more general one, so the idea is you could always start from here. But you don't have to. If you've got a problem where the force is constant, for example, if it's a constant direction, then you can reduce down to this. So it could be that if the direction between the force and displacement is fixed, it could reduce to here. If the force itself is constant, that would come outside the integration. If the angle is constant, that could come outside. So the general formula can simplify down to those simpler formulas that we worked with in those early examples. So I just wanted to come back and take a look at where we stood with this. And we said that now that we have a more general expression for work, we can start looking at forces that are very clearly not constant. So this is not a constant force. We're looking at springs. We're saying how much work is done by a spring force. So in this example, let's start with an unstretched spring. Now we're going to treat the spring as being what we call ideal. An ideal spring being one where I can write the force provided by the spring as minus a spring constant times the amount of stretch or compression. So x could be a stretch, it could be a longer distance that the spring gets stretched out, or it could be a compression where the spring is shortened. And again, it's important to keep track of that reference where the spring is its unstretched natural length. Let's see, this is asking about work being done. Now, in this example, there's a couple different ways of looking at this. If I reach in and grab hold of that spring and stretch it out, I'm doing work. I am exerting a force on the spring, and that force is being applied over a displacement. Now, I'm transferring energy into the spring, and that energy that transfers in is going to be stored as a potential energy. So I'm exerting a force on this and pulling it out. The force I'm pulling with is in the direction of displacement, and that means I'm transferring energy in. Meanwhile, the object's not picking up speed. What's happening is the force of the spring is taking that energy away and storing it within the spring itself. If I do the compression of the spring, same thing happens. I push on the spring. The force I'm exerting on the spring is in the direction of displacement. And so I'm transferring energy into the spring, but it doesn't pick up speed. It turns out not to be kinetic energy. It turns out to be stored within the spring itself. Okay. So let's look at some examples, and we'll see how these problems get set up then. So here is a diagram. Now, we looked at these graphs last time. We said that we could take the force as a function of displacement, and if we plot that, the area under the curve would give us the work. It would tell us how much energy has been transferred. So for an ideal spring, see what we've got here. So this is really complicated here, but let's see what the steps are here. So the work, the energy being transferred by force P. Now that was the pull, remember? So they start right out saying that we're going to be looking not so much at the force being provided by the spring itself, but the force of the hand pulling the spring outwards. Okay, so something is pulling the spring out. Now that force, they're going to say, is in the x direction, so they're designating that as unit vector I. And then they're going to carry out a dot product, and this represents the displacement. So let's take a look at that formula. Okay, so what we've got to do is we've got to get a way to designate force as a vector, and we've got to designate the displacements, the infinitesimal displacements, as a vector. And that's what they've done here. So the I is a unit vector in the x direction, and the magnitude here down lower becomes k times x. So in this step, what they've done is they've written this as a unit vector, unit vector. What would I dot I be? If I take the dot product of two unit vectors, that's going to be 1. So the dot product I times I would be the magnitude of the first vector times the magnitude of the second. Now the magnitude of I is 1, and the magnitude of I is 1, and then the angle between them is 0. So the dot product of I and I is just a factor of 1, and that means the vectors can all drop out. So what this part of the formula, now they're doing this in a lot of detail, the dot product of this formula leaves us with just the force times dx. So the magnitudes remain. Now the limits of integration, they're saying, is we're going to start off at some location that we call 0, and the final location will be x. Now that's important for a spring, that we're clear about where x equals 0 is, because if you remember from the earlier diagram, x equals 0 needed to be the unstretched distance. So it's not just arbitrary where we pick x equals 0. We have to define it that way so that we can use this force expression. So coming back to here, what we have now is integrating from limits 0 to x, the force, kx, required to compress or stretch out the spring, times the displacement. We'll integrate that. The integral of x dx is 1/2 x squared. K is just a constant. And when we carry out the integration, we get a formula of 1/2 kx squared. Now, before we were advertising the fact that the area under the curve is also a way to graphically, visually keep track of how much energy has been stored in the spring, how much work has been done, and that work being done will be stored energy in the spring. So in this case, the plot gives us a right triangle, and hey, a right triangle has an area of 1/2 height times base. 1/2 kx times x. Oh, it's the same thing. It's got to be. It's really just a way of double checking our results. So yeah, for an ideal spring, this is how much energy will be stored. This is how much work we would have to invest, how much energy we'd have to transfer in order to compress the spring or to stretch it out. All right, here's an example, work done by a varying force. It's on a spring. The person pulls on a spring stretching at 3 centimeters. At 3 centimeters, the person finds that they are exerting a force of 75 newtons. So at first the spring was easy to pull, right? That first centimeter wasn't as hard, and then the second centimeter got harder, and the third centimeter was the hardest, and if you pulled at 4 centimeters, it's going to be even harder. So that's what we said the behavior for an ideal spring would be. It just gets harder and harder to pull it as you pull it farther and farther. Now in part B it says, if instead the person compresses the spring 3 centimeters, how much work does the person do? I think it's the same if it's an ideal spring, right? And we can easily imagine springs that are non-ideal. Did they say it's ideal? No, they should really say that. Okay, here's the example. Here is the spring. Now look, I drew all my pictures. I drew the same 3 pictures they drew. Here is x equals 0. I think it's good to draw that x equals 0 picture and go, okay, here's our starting point. Spring has not been stretched yet. Get all the coordinate system defined. Be really clear about your coordinate system. All right, in the first one I pulled it out. 1, 2, 3 centimeters. I'm going to use this formula, f times dx. If it's ideal, which it's got to be for us to solve this problem, f is equal to kx. I plug those values in. It's just kind of the integration that we saw before. This is the amount of work we're going to need to do. Now, I don't know what k is. I know that x is 3 centimeters. They never told us what k is. How am I going to find out what k is? And they told us that by the time we have pulled this out 3 centimeters, the force required to hold it at that location is going to be 75 newtons. So I'm going to do this. I'm going to take that f equals kx. Notice it's not minus kx. F is equal to k times x. So that means that I could calculate a force constant, the spring constant, using the information that they have provided. And that would be the force divided by x. That would be 75 newtons divided by the 3 centimeters. And what that tells me is this spring is pretty stiff. Okay? It is a 2,500 Newton per meter spring. Now, notice that's in standard units, and the spring probably doesn't, it's not going to stretch out by a meter, but it's saying that if this force continued to become more and more difficult to stretch, by the time we had stretched it a meter, that would take 2,500 newtons. Now, there's going to be a range, with any spring, there's going to be a range of distances, displacements that you're able to actually stretch out the spring. It's not going to, if the spring is this big, I'm not going to stretch it out 5 or 10 meters. All right, so the work is 1/2 k. We figured the k value, that's important, times x squared, and that's my 3 centimeters. It worked out to be 1.125 joules, so not so much energy. That's a pretty modest amount of energy, and yeah, if we compress it, if it's an ideal spring, then the k, the spring constant, is the same for compression and for stretching. Okay? Again, it's ideal. We're making approximations here. So we're going to end up storing the same amount of energy in both cases. All right, we are going to ask ourselves, when we do transfer energy to objects, how much speed do they require? Now, what we can do is this, and we'll come back and take a look. Remember, we said all this energy stuff that we're talking about, you could go back and to chapter 4 or 5 and analyze the forces, calculate the accelerations, use the accelerations to calculate velocities, and then you could calculate this all in terms of the speed. Now, when you do that, and it's not showing the details here, we're going to have to come back and do this. For this car, when it started out at some speed, and then we sped it up, we hit the accelerator, and so the forces being provided by the pavement onto our tires, and it looks like this maybe is a front-wheel drive car. No, not clear. But let's say it's a front-wheel drive car, and so these wheels are being forcefully turned, and that sets up a force with the pavement, and the pavement pushes the car forward. Let's say that the car goes from speed v1 and picks up speed all the way to v2. What we can do is if we go through and show the amount of work that we have invested, the amount of work that the car has done, or let's say this, the amount of work that F net has done, what that will show up as is 1/2 mv squared. Okay, so again, we haven't derived this yet, but it turns out that when we do the work, the energy that we have here is more than the energy we had here, and the energy expression looks like this, and so we call that kinetic energy. It turns out that when we do these work calculations, we're going to get an acceleration, we can calculate how much the velocity goes up, and we find that the work is always related by this formula, the net work, as to what the velocities were. And so we're going to designate this as, we're going to call this big K. It's not little k. I know there was a little k in this chapter too, but now we got a big K, and big K is kinetic energy. Okay, and that's staying around with us. We're going to be looking at kinetic energies the rest of this course, all the way through Physics 4B and 4C. Kinetic energy is a very important concept for us. Now, kinetic energy depends on the mass of the object, and it depends on the velocity. The kinetic energy formula we have written down here, 1/2 mv squared. I can plug numbers in, I can put the mass in kilograms, maybe the car's 1,500 kilograms. I can put in the velocities, maybe it's going 30 meters per second, and I can calculate how many joules of kinetic energy we have. Now, when we get into Physics 4C and special relativity, we find out that this is really an approximate formula for kinetic energy. This works really, really well, as long as objects are not traveling too fast. But once you have objects that are traveling fast, once you have them traveling at speeds where kind of the same order of magnitude as the speed of light, it doesn't have to be traveling at light speed, but once you get to 5–10% of the speed of light, it turns out that this formula begins to be, it's no longer correct. It no longer gives us a good approximation. So this is kind of our low speed approximation. And again, in Physics 4C, put a little advertisement out here for Physics 4C, we'll go back and we'll get the updated, corrected formulas for kinetic energy that we are able to derive using special relativity versus Newton's laws of motion. Okay, this is all deriving from Newton's laws of motion, which turn out to be a low velocity approximation. All right, here it is. Here is the derivation. So here is an object. It's got mass m. It corresponds to that car, I guess, or the crates we've been looking at. There are forces of gravity, normal force, and it's being pulled forward. Now, if that's the person pulling the crate, then that's force F. In the previous example we just looked at, the car, it was the force of the pavement pushing the car forward. Let's go back to chapter 4. That will result in an acceleration. Now, an acceleration is written as dv dt. That's our definition. And as long as everything stays one-dimensional, that works. We could expand this to 3 dimensions, but for right now, we'll just stick with 1 dimension and ask how the acceleration could be written. Now, it turns out that when we're looking at energy and work, we're not really interested in how much time things are taking. If you think back about all the examples in the chapter so far, we never mentioned time. We just mentioned locations. We said we started here, and we moved to this location, and it required a certain amount of work. We started here, and we ended up over here, a distance away, and that required a certain amount of energy transfer. So energy is more closely related to displacements than it is to time. And so what we do is we use a mathematical trick here. We can take dv dt, and we can multiply the top by dx, and we can multiply the bottom by dx. Now remember, the dx's and the dv's and the dt's, they can just be moved around like variables. What this is saying is, during a short interval of time, the object displaces by a small distance, and the velocity varies by a small amount. That's what the dt's, the dx's, and the dv's are all about. Just those, what happens during that short interval of time that we have here. Okay, so I'm going to use this definition of acceleration with the extra dx's and dv's. Let's see. Yeah, actually, let me follow this a little farther here. So the dv dx, I'm just going to keep that, but dx dt can be rewritten as v. Now that's a little unusual here, but let's just follow this through. If I were to say acceleration is equal to dv dx times v, I could integrate both sides of that. What I could do is I could take the dx over and integrate both sides. What that would leave me with on the left is a times dx. I'm going to multiply both sides by dx. So the left side now is a dx. The right side is v dv. And we can integrate both of those from, I'm going to integrate from x naught to x, and I'll integrate from v naught to v, and we're going to do this for a constant a. So if a is constant, now this is a general formula here, but let's imagine that we have constant acceleration going on. If the acceleration is constant, then ax, evaluated from between x naught and x on the left, 1/2 v squared evaluated between v naught and v on the right, that would give us a times x minus x naught equals 1/2 v squared minus v naught squared. That would give us one of our constant acceleration formulas. So this formula right here, if you remember from, I'm sure you do, from chapter 2, v squared is equal to v naught squared plus 2ax minus x naught. It's kind of, we derived it differently back in chapter 2, but now we're going right to the source and saying we could start from this definition right here for acceleration, carry through these integrations. If the acceleration is constant, that's how the velocities and displacements are related. And notice there's no time in that formula. T doesn't show up, and that's because we took t out in this step right there. Now, how does that apply to what we're looking at right now? What we can do is we can say that for this, the acceleration is equal to F over m. So the force then could be written as equal to m times a, and that says that the force could be set equal to m times v dv dx. So this is what's happening in terms of motion, and this is the force being applied. So we're relating the force to the changes in motion that will occur as a result of that force. So this is going to become f dx is equal to mv dv, and what happens when we integrate these two sides? Well, this becomes the integral of f dx. You know what the integral of f dx is? That's work. And the other side becomes m times the integral of v dv between v1 and v2. Now, the left side became the net work. The right side became 1/2 mv squared evaluated between v1 and v2. That says that the energy transfer that we provide ends up changing the velocity according to this formula. I'm going to write this as k2, I'm going to write this as k1, and it says that work is an energy transfer. So however much work, if we take all of the forces and combine all of the energy transfers that they're providing for the object, that will show up as an increase or a decrease in kinetic energy. It's going to be equal to delta K. So kinetic energy, we can think of, changing kinetic energy is a result of the work done by the forces that we have present there. So that's kind of the derivation of this kinetic energy work formula. All right, kinetic energy work energy principle is what we're going to, what the book's going to be calling this, and it says that when we calculate all the work, now we've been doing that through the chapter and we did okay. So we're now at a point where we can calculate the work that we're doing. That's going to show up as either taking kinetic energy away or adding kinetic energy into the object, and that will show up as a difference in kinetic energy. So we can use this. We can use this formula in place of using all the forces and accelerations and velocity calculations. So in many examples, as I was saying in the previous lecture, you can use ideas from chapter 3, or let me say chapter 4 and 5. You can look at forces and accelerations, or we can calculate this in terms of energy. And I would say practice both, okay? So here's an example. Here's a hammer, and it's hammering on a nail, and the nail is right here, and there's going to be some distance that the nail gets pushed into the wood, and what we're going to say then is that the force times the distance is going to represent an energy that's been transferred. Now, doesn't really mention the hammer here. Anyway, it's just an example of work being done. Now, the work calculations, or the kinetic energies, are also going to come out in joules. Okay, so those are going to be the units that we're going to have. So with this example, we have a baseball, and what's happening is we're transferring energy to the baseball. There's work being done on a baseball, and what's going to happen is it's going to end up with some kinetic energy. So the baseball's mass is 145 grams. It's thrown so that it acquires a speed of 25 meters per second. Now we've been showing that the kinetic energies formula, this is it. It's the kinetic energy is 1/2 mv squared. So that's going to tell me how much kinetic energy I have in that object. So we've got that information. From the information given, we should be able to calculate how much kinetic energy. And then in part B, is it says what was the net work acting on the baseball. And so here's what we've got. So here's the baseball. It's got a certain mass to it. There's a force acting on it. And as a result, the baseball is going to pick up speed. And that's what we saw in that very first example that we started with at the beginning of the chapter. That very first picture, the A's pitcher was out on the mound throwing this baseball, and the baseball was picking up speed. So by the time the pitcher lets go, it's going at 25 meters per second. And so that's, 70, 80 miles an hour or something like that. Maybe. Is that right? I don't think it is. 25 meters per second is more like 50, 55, yeah, maybe 55 or 60 miles an hour. 145 grams of baseball. I'm going to write that as 0.145 kilograms. And then the velocity here is at 25. I'm plugging that in. So here's the formula. Now, we're going to use this a lot. So K equals 1/2 mv squared. That's a perfectly fine starting point for all this. When they ask how much kinetic energy does the object have, we can take the 1/2 times the mass, that's in standard units, velocity, that's in standard units. If I take kilograms times meters squared divided by seconds squared, that is going to give me joules. That's a capital J. So those are the units for kinetic energy. Those are going to be in joules. So we have joules as the unit of kinetic energy. And the kinetic energy formula, then I plugged everything in, 45.3 joules. So this baseball, traveling at 55, 60 miles an hour, has a kinetic energy of 45.3 joules. So in part B, it says, well, if we look at all the forces acting on the baseball and all the energy that was transferred into it, how much energy must have been transferred into it due to all the forces, and it's got to match up. So if I see something moving at 45.3 with a kinetic energy of 45.3 joules, and it started out with none, in that first picture that we looked at in the book, the baseball had no velocity, had no kinetic energy at all, and at the end of the throw, it now has 45.3. This must be the work done by the forces acting on that baseball. Now, if this is the force exclusively in the direction, then all the energy transfer, all the work was done by that force. That's the force that sped up the baseball in this example. Okay, so here's another example. Let's say that we've got a car. It's initially traveling at 20 meters per second, and we would like it to travel at 30 meters per second. You don't want this to speed up. It's going like, 45 miles an hour, and we want it to speed up to like 67 miles an hour, something like that. So what's it going to take to get a car that's traveling at 20 in order to pick up speed? How much energy is that going to require? How much work is that going to require? Now, where's the work coming from on the car? So we got to practice with these force diagrams too. Is gravity going to be providing the energy? And you go, no, it's a level surface. Gravity's not going to help speed up the car. What about the normal force? And you go, no, normal force is vertical, and we need the car to pick up speed in the forward direction. We need a force in the direction that the car is speeding up. So I'm gonna, in the direction where the displacement is. So the displacement is in the x direction. We need a force in that direction. And the force we're going to be looking at is the force of the pavement pushing on the tires. That's how we exert forces on the car. So let's see what this looks like. And yeah, here's the force diagram. So let's say that, did they say it was 1,000 kilograms? They did. Okay, good. Okay, checking. So, couldn't remember if I put that number in or not. So the mass here is 1,000 kilograms. I want to make it match their diagram. I'm starting out already going 20 meters per second. So the car already has some kinetic energy, right? It has kinetic energy to start with. And we want to pick it up so it has more, even more kinetic energy. Now, even before I draw any of these force diagrams, I can take the M and the V1 and the V2, and I can calculate kinetic energies before and after. So how much kinetic energy did we have in picture 1? How much kinetic energy do we have in picture 2? And so kinetic energy in picture 1, that would be 1/2 mv1 squared. And in picture 2, we're going faster. The mass is the same, but we put in the higher speed. And let's see, there's a factor of 1/2 out front. There is the mass, 1,000 kilograms, the car's mass is. And at 20 meters per second, and we got to square that, that calculation gave me, I think I got this right, 200,000 joules. So the car starts out, already has 200,000 joules, 200 kilojoules of energy, and at the higher speed, it's going to need to have 450,000 joules, again, of kinetic energy. So we're working just directly in terms of kinetic energy calculations, and again, I didn't have to draw any force diagrams. I just had to know M, V1, and V2 to find out kinetic energy before and after, and what would those values be. So I've got my values here, and it says that what I'm going to need then is I'm going to need to come up with a net energy transfer into the car of the difference between those two. So that would be 450,000 minus 200,000. That means I have to come up with 250,000 joules. That is the energy that needs to be transferred in. I'll write that as 250 kilojoules. Well, let's go back to the force diagrams now and see what's going on. Here's the car. Let's say that we have the force of the pavement pushing the car forward. Now that's a frictional force. It's a static frictional force being used to push the car forward. There could also be static frictional forces opposing us. So there's going to be air resistance, which is not strictly speaking friction, but there's air resistance. There are going to be frictional effects due to, we're going to lubricate the hubs in here best we can, but there's going to be some frictional effects also. So I got friction driving me forward, but I also going to have frictional forces opposing that, and I can have air resistance. So let's say this is the force coming from the engine, rotating the tires, setting up the forces here. That's a static friction force. And we'll just let this represent all of the resistive forces acting on the car. Now I've also got gravity and I got a normal force. Which of those is going to provide the 250,000 joules of work? one of those forces has to transfer work, provide work, and energy transfer into the car. And the direction of displacement is here. So here's V1, there is V2. I need a force specifically in the direction of displacement. Now, the force, big F, coming from the tires in contact with the roadway, that's the force we're going to depend on to accelerate the car. That's going to need to transfer some work, transfer some energy. N and mg are not going to be involved in this because it's a horizontal, level roadway, and on level roadways, the displacements are horizontal. Gravity and normal forces are not making a contribution to energy transfers for this. And so friction would still be involved. So what we could do is this. We could come back to our definition of work. We could write it as a dot product here. We have to think in terms of the net work being done. That would be combining all of these. Now we've already kind of ruled out gravity. That's not going to contribute. We ruled out the normal force. That's not going to contribute. So they could, if we were on an incline, then we could have gravity also playing a role. But for this example, normal force won't contribute, gravity won't contribute. It's going to come down to the forward force driving the car forward minus, that's going to be a negative value, we're going to have to subtract off a certain amount of energy that friction is taking out of the system. In any case, when we calculate all of these together, what we know from the numbers given is that the net work is the 250,000 joules. That's why the car is speeding up. Okay, now what about the work required to stop the car? We said that we have a car that sped up to some speed, but now it's going already at 60 kilometers per hour, but we would like to slow it down. So we would like to have it drop down from 60 kilometers per hour down to 0, and we would like to determine what the stopping distance might be. And the stopping distance here is listed as 20 meters. So if we try out our brakes and we're able to stop with 20 meters if we're going 60 miles an hour, what happens if we're going 120 miles an hour? What happens if we're going twice as fast? If I'm going twice as fast, will the distance, stopping distance, will the stopping distance be twice as long? Maybe that makes sense, maybe it doesn't. I think we should look at the math and find out if that's a reasonable assumption to make. So here's the car. Now the velocity is in this direction. So let's get a velocity arrow here. There's a frictional force slowing things down. There's a normal force here, there's a gravitational force here. The displacement is going to be in the forward direction. So we could put a little arrow on that too. So the displacement specifically is to the right in my diagram. Now what's going to happen here is the normal force is not going to transfer any energy, and gravitation is not going to transfer any energy in this example because they're perpendicular to the displacement. Now what is going to transfer energy is friction. Now because the frictional force is exactly opposite the displacement, what we'll write that as is F times D, but I'm going to put a minus sign in right there. What that minus sign represents is the cosine of 180 degrees. So if I use a dot product, I have to have a cosine theta here. The theta is 180, cosine of 180 is minus 1. That's one way to keep track of it. Once I've done a few of these problems, and I can see that typically what happens is the friction is just going to take energy out. Okay. Now the frictional force here, it's a static frictional force because I'm not going to skid my car. I'm going to brake it responsibly. In fact, my car has an anti-lock braking system, so it won't let me skid the car. I think it has that. Maybe I should try and find out. But what that's going to become is a static frictional force. Now, ideally, I'm using as much of that static friction as is available. So what I could do is I could write that as kind of the peak value of static friction, and that would be equal to mu sub s times n. And you're thinking, oh my gosh, chapter 5 stuff? What's chapter 5 stuff doing in here? But it's definitely part of what we're looking at here. So I've gone back and I've brought back all those frictional force formulas. The maximum value then can be written as mu sub s times n. N is equal to mg. So if I look at my diagram here, n is exactly opposite mg. It's on a horizontal surface. N is equal to mg, and that tells us that the frictional force then can be written as mu sub s times mg. So let's bring that over. I know I wrote independent of velocity here. Oh, the frictional force, that's right. So we're treating this as the friction force will be constant. I've got a constant frictional force that will be slowing me down. So the work, I'm going to write this in energy terms. The work that I need to slow the car is going to, the amount of work I need to take or transfer out of the car is the total kinetic energy. Now the total kinetic energy of the car is 1/2 mv squared, where, oh, the v was, okay, let's go back and look at the v's. In the first case, it was 60 kilometers per hour. In case 2, it's going to be 120. So our question was, we start here at 60 kilometers per hour. We're going to double the speed that we start with. What's going to happen to the stopping distance? So I'm just going to do a ratio. What I'm going to do is I'm going to take the energy that friction is taking out. Now we decided that was F times D. It's a negative value, but we're interested now in just finding out how much energy. So I put some absolute magnitude signs on this. So the absolute value signs are telling us how much friction. That's going to equal the kinetic energy. That's going to equal 1/2 mv squared. So F times D, the frictional force, times the distance, is going to equal 1/2 mv squared. And the frictional force is going to be the same in both cases. So for case 1, I'm going to have the same frictional force as for case 2. So what I can do now with this ratio is I can cancel out the frictional force. Frictional force is going to be the same both times. And on the other side, I can cancel out the car's mass. Car's mass is going to be the same. The 1/2 will cancel out. And what I'm left with, I took this ratio of formulas, I flipped it over to say the distance required for stopping in case number 2 divided by the distance required for stopping in case number 1 is apparently going to be given by v2 squared divided by v1 squared. So I've eliminated everything else, the mass of the car, the frictional force. It comes down to the ratio of distances equals the ratio of velocities squared. Now, the velocities they gave us were 120 kilometers per hour versus 60 kilometers per hour. That's a factor of 2, and it's going to get squared. So that's kind of interesting. What we can think of is, all right, if we think in energy terms, a car going twice as fast, how does that relate to the kinetic energy? And if a car goes twice as fast, it'll have 4 times as much kinetic energy. Okay, so that means getting the car up to speed requires 4 times the energy, and bringing it to a stop means removing 4 times as much energy. So since the force, the frictional force we're using, is the same in both cases, the distance is going to have to be larger by a factor of 4. So if the velocity goes up by a factor of 2, kinetic energy goes up by a factor of 4, and that means I'm going to require 4 times as much distance to stop the car. Now this is one of those DMV questions, right? You go to the DMV and you take those tests for your driver license. Don't they ask that? I can't read. They haven't required me to take a test for a while, which maybe they should. But you know, we could write some of these formulas down on it, and you could derive the formulas for it. When you're, I think that's one of the questions, right? Would they ask you if you're going twice as fast, how much additional stopping distance are you going to need? And it's going to be 4 times as much. So it's the square of whatever the ratio is for the velocities, and that's because kinetic energies depend on velocity square, and when we brake, we're taking the kinetic energy away from the car, proportional to distance. Okay, something to keep track of when you're out driving, right? Okay, so here's one more example. We've got a compressed spring. So the example here, and this one I better read carefully. It says that we have a spring set up, it's horizontal, we have a block next to it. The spring constant, okay, so that's the first piece of information I want to make sure I'm clear on. Actually, I want to make sure it's horizontal. 360 newtons per meter. So it looks something like this. Now, it says how much work would be required to compress it from the uncompressed length. So the spring's going to start off uncompressed. And we're going to draw diagrams for this, and for sure, one of those diagrams is going to show an uncompressed spring, because that's what you got to do on these diagrams, I feel like. So now we're going to go from the spring being uncompressed to being compressed 11 centimeters. So that sounds doable, right? We know the spring constant. We know how much we want to compress it. Yeah, we can calculate how much work is required to compress the spring. Now what's going to happen next is we are going to take a 1.85 kilogram block, there's the block right there, and we're going to place it up against the spring. So we push the spring back, we place a block in front of where the spring is while holding the spring in place. And then, once everything's set up, we will let go of the block, and we would like to predict how fast will the block be traveling once it gets back to the spring's natural length. So so here's what happens. We've got the spring compressed. Here is the spring pushing on the block. Now notice what they're saying here. Again, the force that the spring is providing to the block is k times x. They're treating x as a positive number, and the k, of course, is a positive number too. So be careful with signs here. Often we just go back to using positive signs for everything. So they're saying both that x is positive. So kind of what they're saying is, this is the positive direction for x, but this is the positive direction for force. And that's fine. I mean, the bottom line here is you've got to decide how to set the problem up so that the signs will make sense. So we've got a gravitational force here too, probably not going to get involved in this. The normal force here too, again, that's probably not going to be so relevant. We're on a level surface. It says we're going to calculate it once, where we just let go, and it picks up speed, and we're treating the surface as frictionless. So in part A, A was just the work, B is how fast, ignore friction, that's what I was looking for. Ignore friction on part B. In part C, we're going to come back, and we're going to do the whole problem again, but this time, there's a drag force. So I guess that's air resistance. They're saying that it could be friction. I'm surprised that's the thing. So there's a resistive force of some type in the second example. All right, let's take a look at this. So here's the block. Here are all the forces drawn in. Now notice I'm just going to draw this as kx. Okay, so here is the spring. It's been compressed. I'm going to do part A first. So I did put the frictional force in here. Let's just calculate how much work is going to be required. We determined this. We actually went through the derivation for a spring twice. And so at this point, if you need to review that, go back and take a look by all means. I'm just writing the formula down, but you want to really understand where this is coming from. So if you don't remember how we got 1/2 kx squared, go back, take a look at that example. Now, I'm putting in the force constant. That was information that was given. So that should be right here. So let's write that in. K is equal to 360 newtons per meter. So I've got the 1/2, I got the K, I've got the x squared. Now the amount that it was compressed is 0.11 meters. And putting all those numbers together, let's see what happens here. I got meters squared divided by meters. That leaves me with newtons times meters. And if you remember, newtons times meters are joules. So that's going to give us 2.18 joules of spring potential energy. So I'm going to have that much potential energy stored up in the spring when I've compressed it 11 centimeters. Okay, so we want to, that's going to be the energy we're working from. Now, when we let go, the spring will return all of that energy to the block. So all the energy we stored up in the spring now is going to transfer that into the block. Now, since it's an ideal spring, the energy that we stored all comes back. Now, if you guys, if you've played around with springs, you know that if you stretch a spring out and it warms up. So what happens when you stretch a spring and compress it and stretch it and compress it, some of the energy that you might think is being stored in the spring actually goes into thermal energy. So again, one of the features of an ideal spring is that it returns all the energy that it was given. All the energy that was stored in the spring is going to come back out of the spring. It's going to be available. And for real life springs, that may not be the case. But we're going to go ahead and say it's ideal. All of the energy that we stored when we compress the spring is going to get returned into kinetic energy of the block. So the kinetic energy of the block is going to be 2.18 joules. Now I know the mass of the block, and I know the formula for kinetic energy. How could I ever come up with velocity? And this is an important formula. V is equal to 2k over m to the 1/2. Now this formula is the kinetic energy formula solved for V. And it's amazing how students, the 1/2 mv squared, not an issue. Everybody knows kinetic energy is 1/2 mv squared. But this formula, when I show this to students go, wow, what is that? I don't see what that's. So these are the same formula. Just remember, that's what it looks like when you're solving for velocity. So the velocity here then, we're going to say 2 times, and I put in all the energy. The kinetic energy then is 2.18. And then I divided through by the mass, took a square root, and it's predicting a speed of 1.53 meters per second. That's how fast the block will be traveling once it separates from the spring. Now, could we have done this using accelerations? Absolutely. And I would recommend, practice this example on your own using energy, and then maybe go back and see if you can get the same answer using the acceleration formulas that we've worked from before. Now, the acceleration here, this is a warning, the acceleration here is not constant. The acceleration is varying because the force is varying. So in this case, kx is not a constant force. It's changing as x changes. And so it's not necessarily an easy problem to do in terms of accelerations, and that's one of the reasons why we're demonstrating that with energy, using energy conservation is what we call it. By using energy techniques, we are able to go in and solve for the velocity, we never had to go in and determine what accelerations might be, or we didn't have to solve for the velocity that way. One way you might think about this, remember when we derived this expression for kinetic energy, it involved carrying out integrations of the velocities. And once we have the formula, one way to think about this is I don't have to go back and redo the integration because we already did it. So once we've done the integration and established that the kinetic energy is given by 1/2 mv squared, then anytime I calculate how much energy is present, I can go directly into kinetic energy. I don't have to set up a, well, I'm going to have to set up a force diagram maybe to be clear about some of the directions. So I'm going to put a, maybe I can get by without a force diagram, or maybe I should, actually continue using the force diagrams. But you can work entirely in terms of energy for this. So this worked out to be 1.53. Now in part C of the problem, what they said is, now what would happen if we put a little friction in? So let's do that. Let's put a little bit of frictional force or some kind of a resistive force. Now they told us this was constant, and it's a constant force of 7 newtons. Now, I didn't calculate any of the other forces. I guess I could have. I could have calculated gravity, could have calculated normal force. I could have done a plot, a graph, showing what the spring force would look like. For the energy, for the work being removed by friction, I'm going to write that again as minus friction times d. So what happens is the frictional force is acting along the entire 11 centimeters, and the force is 7 newtons. Now, I took the 11 centimeters and converted that into meters. It says that along the way, the frictional force will remove. It's going to take energy out, and by the amount of 0.77 joules. Now remember, when we compressed the spring, how much energy did we store in there? And the energy that we stored was 2.18 joules. But now on the way out, friction is going to be removing 0.77 of those joules. So I can take, so we're just doing energy here, I can take the 2.18 joules of energy that I had to work with and say, it's not all going to be kinetic. I got to subtract off the energy I'm going to lose due to friction. So this was the energy stored in the spring. This energy gets lost as the block runs along the surface. So by the time the block just separates from the spring, it only has 1.41 joules of energy. Now, if the friction continues, if I have friction all along this surface, that block is going to slow down. So it's not going to go on and on forever. In part B, where we said it was a completely frictionless surface, which is not very realistic, the block would continue moving at 1.53 meters per second. But in the lower case, where we do have friction, right at the point where the block separates from the spring, we have 1.41 joules left. Putting that into our velocity formula, I can put in the kinetic energy and the mass. It says that the speed now will only be 1.23. So that's how much difference between no friction on the way out versus a modest amount of friction that the block has to get past. And then again, for this second case, that's not going to be, in this case, there's no friction. So that speed the block continues with forever and ever. As long as there's no friction and the surface is level, it maintains that speed. But in this case, if the friction persists beyond the location of the spring, that's going to slow down. Okay, so it would continue to slow down in that case. Okay, questions on any of that? That's it's a good amount of detail. I mean, the examples that we've brought out are I think pretty important. I think, you know, this energy stuff is new. We have another chapter coming up, chapter 8, where we'll be looking more at energy concepts. And what you want to do is as you're going through these problems, you know, practice thinking in terms of energy. I think it's a fairly challenging part of the course is thinking in terms of this new concept of energy. It's a little abstract. You know, when we looked at all the forces and velocities and accelerations, those had, I think, more of an easier way to kind of have an intuition about those, and energies keeping track of the same, but a lot of times it's not as obvious. Okay, so that is the example. Ooh, that's the summary of chapter 7. So energy transfer, we introduced the vector diagram, the vector dot product. So we did vector dot products and showed that it's keeping track of that cosine theta factor. When we looked at variable forces, we needed to come in and calculate the work as an integration of a dot product or an integration of a force, an angle, and a displacement. And then the kinetic energy formula, that's going to get used a lot. So K is equal to 1/2 mv squared. That's our kinetic energy for this. Now, what we find then is that, you know, we spent kind of the first half of the chapter finding out how to calculate energy transfers, work, based on individual, you know, forces one by one. And I think I remember saying, practice listing all of the forces, and then list how much work is being done by each of those forces. When we add that all together, that will show up as an increase or decrease in kinetic energy, or if W net's 0, then the kinetic energy remains fixed. And then the kinetic energy formulas. Okay, so any kind of questions at all, stop by office hours. We'll get those looked at. All right, that wraps up chapter 7. On to more energy.